It's science, but not as you know it. The Naked Scientists.
Hello, welcome to The Naked Scientists this week with Chris Smith, that's me, and also with Helen Scales. Hello, Helen.
Hello.
Now, coming up this week, jazz musicians have gone into the brain scanner to reveal what happens in their heads when they improvise. Also, what have sharks' hunting habits and a shopper in a supermarket got in common? Well, apparently, it's the way they walk. Wouldn't the Bee Gees be proud of them? And also, BatNav. Scientists have discovered how bats use the Earth's magnetic field to find their way home. But they didn't in this case, because they got put into a magnet and got magnetised the wrong way, and they all flew off in the wrong direction. That's all coming up. See you in a second with that.
Thanks, Chris. Now, this week we're also tuning into the science of sound and music. David Howard from York University is here to explain how the voice works, where accents come from, and how an impersonator can sound so like a person that they're taking off you just don't know the difference. And music to your ears, or maybe not. How the brain responds to music and why some tunes border on the intolerable.
You know, the American government drove Manuel Noriega out of his compound by playing him 36 hours of AC/DC music. That was enough to drive him to surrender. And I think we've all had that experience where you're in a shopping mall or something and they're piping in music and you wish it would just stop.
Haven't we just? I've certainly had that experience. But on a more cheerful note, Ian Cross is with us from Cambridge University to talk about the early origins of music and what it means to different cultures. Chris.
Thank you, Helen. So if you've got a question for us about the science of sound or music, then do get in touch. Email chris@thenakedscientist.com.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider, on the web at ukfast.net.
Well, let's kick off with a look at this week's top science news stories, and a fantastic thing that I saw this week in the journal PLOS ONE, Helen, and it caught my eye because I knew we were going to be talking about the science of music, and that is a study on jazz and other kinds of musicians when they improvise. Because as one of the researchers in this case points out, and that's a guy called Charles Lim, who with his co-researcher Alan Braun has done this study, when they play, this is jazz musicians, they have their eyes closed and they do so in a very distinctive personal style that transcends traditional rules of melody and rhythm. And so what he's saying is that people who play and then improvise start to generate funny combinations of notes and music which has never been heard or played before, and it all makes sense, but it's very distinctive to that individual, and they wanted to know what was going on in the minds of the people who were doing that. And so they put them in the brain scanner. That's
fantastic.
The logical thing to do.
With their saxophones?
No. The way they did this was with fMRI, that's functional magnetic resonance imaging, and this uses a very powerful magnet, so you can't just put anything metal near it, because if it's magnetic, it could have a catastrophic effect on the person in the scanner and also the scanner itself. So they had to redesign a keyboard specially so this could be done. So they built them a special little keyboard to play on and then fed back to them what they should be hearing through specially adapted earphones. And the first thing they asked them to do, and this is 6 trained jazz players, they said, go into the scanner and first of all, we want you to play some scales from memory and also play some music you've heard before, because what they were looking for was which bits of the brain were going to light up when they were doing just normal music from memory. Because the next thing they asked them to do was start improvising. And then by comparing the 2 brain scans and subtracting the normal bits of the brain that are active when you're making music from memory from the bits that activated when they're improvising, it was possible to tell the difference between which bits of the brain must be making these contributions to improvisation. And there were 2 striking findings, and they both affected the front part of the brain, what's called the prefrontal cortex. This is very, very big in humans, and it's what really sets us apart from other primates. And the regions that they saw differences in was a region called the prefrontal cortex on its dorsolateral aspect, so that's the outside edge of the front of the brain, and this part of the brain is concerned with self-censorship and inhibition. It's the bit of the brain which, if you were a politician undergoing a very taxing interview on a radio programme, it's that bit of the brain that would be active because it would be making you choose your words very carefully. Also, if you're going for a job interview or something. So that's the bit that normally says to people, be careful what you do or what you say. It sort of gates the flow of information out of your brain. And the other bit of the brain, which was, that bit of the brain, I should point out, was much less active, so they switched that off, and they increased the activity in the medial prefrontal cortex, and that's the region of the brain which is concerned with self-expression and individuality. You'd activate that if you were telling a story about yourself. And so what Charles Lim says is, what we think is happening is when you're telling your own musical story, i.e. improvising, you're shutting down impulses that might impede the flow of novel ideas.
I think that's fantastic. Now, I wonder if the same thing happens in other types of artists, like dancers, because I know lots of dancers, and I reckon they improvise in a very similar way. I wonder if that's similar parts of the brain. You need to get them dancing.
You should team up with them, because they say they want to look at precisely that thing. They want to know if poets do the same thing, or other writers. And I suppose that's appropriate because all poetry should scan, shouldn't it?
Oh dear. Oh dear. Well, I couldn't possibly let this news story pass up this week because you know what I'm like with my fish. But this is a lovely story about the sharks of the world. Now, with such a huge blue ocean to wander around, how exactly do these marine predators like sharks find their next meal? Well, it turns out that instead of randomly swimming around waiting to sniff something, which they can admittedly from quite a long way away, sharks and other marine hunters actually move around according to a particular set of rules that mean they're much more likely to bump into something to eat. And it's a similar thing that shoppers will do in supermarkets. Strangely enough, us humans do this too. Now, for a while...
So women at the meat counter do circle like sharks because it's said that they do that just before discount time.
I think you're right. You're right, that's it. But basically, ecologists have studied the hunting behaviour in various animals before, including things like spider monkeys, and they've shown that they use something called a levee walk. Now, there's a rather involved mathematical explanation of what that is, but essentially it means that the animal or person or shopper undergoes a lot of short distant journeys interspersed with fewer longer distant journeys. And then this is a much better way of finding rare prey or meat or pasta, whatever it is in your shops, that's scattered around in clumps across large areas of ocean or supermarket. Now, fishing vessels do this sort of thing as well, and like I say, people in supermarkets have been watched, and also in other kind of shopping scenarios. And it now seems that the open ocean species do the same thing. David Sims from the Plymouth Marine Laboratory here in the UK has led an international team of researchers who collected and analysed lots and lots of diving data from tags that they stuck on 31 different marine creatures, and that included sharks, cod, sea turtles and penguins. And what they found was that 5 out of the 7 different species they tagged performed these levee walks. They did lots of shorter dives, interspersed with some occasional much longer dives. And they also created a virtual ocean, which is a rather lovely idea, on a computer, and showed that these animals are much more likely to encounter prey by doing this kind of diving than if they were sort of simply wandering around randomly.
Why does it work, Helen? Why do they encounter more prey that way?
I think it's something to do with, it's sort of if you think about it in the supermarket setting, if you say you're looking for a certain product, you'll look quite carefully in one area, and if it's not there, you don't just look next door, you think, all right, I'll try the next aisle. So you go over there and have a good look there, and if it's not there, you try somewhere else. So I think it's a combination of spreading yourself around a large area, but then also looking quite carefully in those different areas that you get to, just in case, because you know you're not just going to stumble across it. You have to make sure if it's in that particular area, which is kind of like a cluster of jellyfish for sea turtles, or food for sharks, that kind of thing. They tend to cluster together, but with lots of space in between them.
And the fact that all these different animals do this, does this mean it's sort of genetic? It's hardwired into them to behave like that because they all do it and they're not that related?
I think it basically shows that this is a very good solution to this particular problem that lots of different types of animals face, including us people. So it really must be a very effective way of finding this kind of food. And the nice thing is, it seems this kind of research might help us do other things, like programming robots to select samples in inaccessible parts of volcanoes, perhaps, or even on other planets. And it might even help us understand things like how our ancient ancestors went off and explored and colonised distant shores.
I suppose it might also help if we build a robot that could do our shopping for us. But there you are.
Maybe.
I live in hope. I've got sort of one of those, and she's called my wife.
Oh dear. I don't think
I'm very grateful to her for that. Anyway, getting around to bats now. So from oceans into the air, there's a researcher called Richard Holland, and he works at the University of Leeds, and he's published a paper this week where they've actually got to the bottom of how bats, and probably other animals, are able to follow the Earth's magnetic field to get around, because he showed for the first time about a year ago that bats certainly follow and respond to the Earth's magnetic field, but they didn't know exactly how. Now they think they know. And they took a group of 30 big brown bats. They're actually a species called big brown bats because they're big and brown. And what they did was to divide them into 3 groups. And the first group were not exposed to any magnetism. The second group were put into a magnetic field where they received a pulse of magnetism about 5,000 times stronger than the Earth's magnetic field, but in line with the Earth's magnetic field. And the third group got a pulse of magnetism the opposite direction to the Earth's magnetic field. And the bats were then driven to a place about 20 kilometres from their normal home range and released. And the researchers radio tagged them so they could watch where they went and follow how they tried to make their way home. The ones in the first group that didn't get any magnetism flew straight home. All of the ones in the second group that were magnetised in the same direction as the Earth's field went straight home. The third group, who were magnetised in the reverse direction, half of them went totally the wrong way. And what they think is going on is that it's highly likely. I mean, you can find this in brain cells in pretty much every animal, but certainly in bats, you can find these tiny crystals of the chemical magnetite. Now, this is an oxide of iron, Fe3O4, and these little spicules of magnetic iron form inside cells, and they will swing around like a tiny compass inside nerve cells. And what the researchers think is that when they move, they distort the membrane of the cell, and this adjusts tiny pores in the membrane of the cell, allowing charged particles to flow through inside the cell and either activate it or deactivate it. And in this way, the bats can read the Earth's magnetic field. When they blasted them with a dose of magnetism the opposite way to the Earth's magnetic field, it flipped and remagnetised their compasses. So initially, they flew totally the wrong way until they realised their mistake and then reset their compass.
So they can reset it and then
Yes, they can. And the other cunning thing they can do is to look where the sun is, because they know the sun always rises in the east and sets in the west, and so they always set their compass to the sun. And that was how they would normally reset their internal compass. Why did only half of them do it? The researchers think, well, it could be that these bats use a lot of other cues to find their way around, and it could be because they're quite close to home that the half that didn't go wrong already knew the way home, and so they were just merely overriding their internal compass and following their nose rather than what
maybe
their compass was telling them.
Echolocation or something, that kind of thing.
They have very good eyesight and very good smell too, so they were probably using other cues and other signals, or they were just the males out of the group because it was a mixed group, and they were the ones that wouldn't ask for directions.
Excellent. Well, there are lots of creatures in the world that seem to use this fantastic magnetic sense of direction, and sea turtles are another one. And I'm going to finish off today, I'm afraid, with some slightly discomforting news on an unexpected link between environmental problems on land and those in the sea, because it seems that cutting down rainforests in West Africa is damaging not only areas of forests and all the things that live there, but may also be harming endangered sea turtles. Now, Gabon lies on the Atlantic coast of Africa, around 2/3 of its vast rainforests are now being opened up to logging. The trees are being felled and then they're floated downriver to the coast where they're then exported. But a lot of them these trees are getting washed out to sea and getting lost essentially, but a lot of them ending up on beaches where leatherback turtles are trying to nest. Now, it might seem like a fairly trivial problem to say that a few trees have scattered around a beach, but the effects of this can actually be quite serious. An international team of researchers led by William Lawrence from the Smithsonian Tropical Research Institute in Panama has been studying turtle nesting sites in Gabon and found that between 2002 and 2004, around 10% of the nesting attempts were aborted of these leatherback turtles, which are extremely endangered, because logs were just getting in the way of females that were trying to lay their eggs. They also found that around 1/3 of Pongara Beach, which is probably one of the world's most important leatherback nesting turtles, was clogged up with these logs. Now, conservationists want to see changes put in place to end this wasteful loss of trees, because frankly, if we're going to be chopping down all these trees in the forest, for them to float off and not be used is a huge waste, and also to try and introduce rules to help protect these important turtle nesting sites. One problem is that under current laws, these misplaced logs belong to the Gabon government, so it's illegal to try and move them, and that actually these are incredibly valuable. I think around 11,000 trees are scattered along the coastline, and they could be worth $11 million. So really the situation could be changed partly by banning logging during the turtle nesting time and let people clear the logs off the beaches, but they'll have to do that quite carefully so as not to disrupt those poor nesting sites and let the turtles get on with what they need to do, which is replenish their populations.
It's amazing to think what all the knock-on effects of something so initially apparently trivial as cutting down trees and floating them down a river could be. But it is The Naked Scientists with Chris Smith and Helen Scales. We're talking the sound of music, and coming up very shortly is this week's Kitchen Science, in which we'll be inviting you to make some music alongside the programme. You're going to need a small plastic bottle and some water if you want to do this.
Laying the facts bare. The Naked Scientists.
An email here from Sam Whitehall, and I'd like to ask everyone your opinion on this, because I'm not sure I know the answer. Sam says, I've just been on holiday and I noticed a hand dryer in the toilets, and they always seem to claim that the hand dryers are greener than paper towels. But has anyone, except the hand dryer companies themselves, of course, actually done any studies on this and all the extra energy costs involved in running the heater versus using the paper? So what do you think? If you have any ideas on that, email chris@thenakedscientist.com, and it's of course the same address for anything related to the sound of music. We'll be talking about how the voice works in just a second.
Now, have you ever played around with a bottle and noticed that you can create a nice note, a bit like a flute, if you blow across the top? Well, in this week's Kitchen Science, Mira's taking it one step further.
For Kitchen Science this week, I've come to the engineering department here at the University of Cambridge to meet with Hugh Hunt in his office. Hello, Hugh.
Hello, Mira.
So we've got some quite basic equipment in front of us here today. We've got a bucket and we've got a plastic bottle, just a normal kind of regular size bottle. What are we going to do with this, Hugh?
Well, this is just a sort of a 250ml drinks bottle, and I'm going to blow over the top of it like this to produce a note. Nothing particularly fancy about that. Now, if you put water in the bottle, it's about a third full or thereabouts. Now, we know if we blow now over the top, we get a higher note. And if I empty that out again, I go back to this same lower note.
So we know that if you pour water inside the bottle, the pitch of the sound you get when you blow across the top goes up. What are we going to get the people at home to do now?
A very similar thing. By adding water, we reduce the volume of air inside the bottle. So I'm going to reduce the volume of air by a different method. I'm going to scrunch the bottle up like this. Okay. And what happens when we blow across the bottle then? It's important when you're doing this, it makes it much easier if you hold the bottle by the neck of the bottle. Don't hold it on the side of the bottle. And you'll see if you try doing it on the side of the bottle, it's nowhere near as easy.
OK, so we have to hold it by the neck of the bottle. Got it. What else?
Well, I've got a bucket full of water here. And what I'm going to do is I've got the bottle, just the ordinary unscrunched bottle. And I can actually lower it into the water like this. And I can blow again.
There's no change.
Yeah, that's right. There's no change. The note doesn't change. Well, now, you'll find that when you take the scrunched up bottle, it behaves differently when it's out in the air than when it's submerged in water. So that's another thing for you to have a look at.
OK, so once you've practised blowing across the top of the bottle and know how to get the sound, we've got two things for you to do. Scrunch up the bottle and blow across it again and see if the pitch of the sound changes. And then lower the scrunched up bottle inside a bucket of water and see if there's a change in the pitch there as well. So if you've got a plastic bottle and a bucket of water, give it a go at home and let us know what happens.
Thanks, Mira and Hugh. Now, if you have a bottle and a bucket to hand, have a go, but let us know what happens. Like she said, we want to know. Maybe you can even come live on the air and play to us. Chris@thenakedscientist.com, and we'll find out later what the answer is.
Thank you very much, Helen. Now, we are talking about the science of sound and music this week. We're very pleased to welcome from the University of York, David Howard. Hello, David.
Good evening.
Thank you for coming down and joining us.
Not at all.
Your research, very interesting, is actually on the voice, something that which we on the radio can't do without.
It certainly is, and of course it's something nobody can do without in this day and age.
So how do you go about studying it?
Well, there are a number of things you can do. I mean, the most obvious thing is you can stick a microphone in front of people and look at the wiggles and try and make some sense of them. But that needs to be done in combination with understanding how we create a sound. What are the key parts of our bodies we use when we create a sound? So one of the things we've been looking at in the past is differences between people who sing or speak. So, for example, we've been looking at choristers in cathedrals to try and establish whether people can tell the difference between them singing, and also to try and establish what it is that changes as boys and girls grow older.
So you've given me some samples, so let me invite the audience to participate in a bit of a challenge then. So you've given me two groups of choristers, one all boys, one all girls, singing the same piece of music, and we're going to see if we can get people to tell the difference.
This is correct, but the key thing when you're listening is to realise this is a choir singing, so you need to listen for the top line of the choir.
Okay. So I'll pick one of these at random, so here we go. Any thoughts, Helen?
Just enjoying that. It's rather lovely. I don't know, actually. I think I'm going to need to hear the next one to compare it to. It sounded fairly female to me, I think.
OK, shall I play number 2 then, David?
Yeah, try number 2.
OK. I have to say, I cannot hear the difference myself, and I've done quite a bit of singing in a lot of cathedrals and choirs and things.
Well, I have to confess that I too have, and listened obviously to many children whilst making these recordings. I find it difficult to tell the difference. If you asked me to tell the difference, I'd struggle.
So if I let the cat out of the bag, the one I played first that you gave me was the boys singing.
It was.
And Helen thought it was girls. And the second one was the girls singing. So does this then put the kibosh on this claim that you have to have all-male choirs, and especially all-male treble choirs, little boys, because they sound better than girls?
Well, I believe it does, yes. I mean, what we're demonstrating here is that given the same situation, boys and girls can fulfil the role and do a job as good as each other. But it does come from other areas too, because boys have been singing in cathedrals now for over half a millennium, and girls have been singing since 1991, so they haven't got much of a head start in terms of catching up. But this does show that at Wells Cathedral, which is where these recordings were made, actually girls can do the job as well as boys.
And if you feed those recordings into a computer and ask it to build you a profile of what the voices actually look like, does that give you any obvious standout differences between the boys and the girls?
No, it doesn't. Interestingly, our ability to analyse things for the real subtlety of listening, we cannot yet with a computer do as well as our ears.
Which makes a change, doesn't it?
Well, it doesn't.
We're not being beaten by a computer.
It doesn't. It's rather nice, I think, that we haven't yet beaten the ear.
OK, well, let's actually zoom in on the business end that's what's doing this, the whole vocal tract. So can you just give us a whistle-stop tour of that and how it works?
Well, very briefly, if you're going to make any sound, you need a source of sound. And for most of what we do when we're speaking, it's the vocal folds which vibrate inside the larynx. So that lumpy thing on your neck, the Adam's apple at the front, that you can feel with your finger, and if you put your finger on it and swallow, it moves up and down just to show that it's alive and well. There are two muscles in there that vibrate, and they produce a buzz. Now, I've got an electronic version of a buzz here, so this buzz you're about to hear is an electronic larynx.
It's not a shaver, but it sounds
No, it might sound like one. Here we go. So that's a buzzing sound, and to prove that this stimulates what your or my larynx are doing, I'm now going to tell you my name and use this instead of my normal larynx by placing it against my Adam's apple.
Hello, my name is David Howard.
So how's that working? You're just sending a pulse of sound waves in through your throat, and it's hitting your vocal cords. You're not breathing and talking as you would do normally. You're just moving your voice box as though you were going to...
That's correct. The way you use this is to hold your breath. So you take a breath and go... as if you're going to lift a heavy weight, which closes the vocal folds, jams them together so that you can build up pressure in the lungs just to support yourself. But it also means that when you put the buzz in, it then stimulates the cavities above in the normal way. And the key to speaking is that we have two things available to us. We've got a buzz and we've got a tube. And this tube is a squidgy tube which goes from the larynx to the lips, the mouth tube. And, of course, when we're talking, we're moving our jaw, tongue, lips, and that changes the shape of the tube and therefore changes the acoustic characteristics of that tube.
So can you model that? If you take measurements from somebody and record over time, can you build up a sort of profile of what their throat looks like so it's possible to recreate their voice almost?
You can, and this is something we're now doing. This is looking at how can we electronically synthesise a natural-sounding human, starting with the real tube shape of a human being. So you put them into a magnetic resonance imaging machine, and if you do that and characterise the tube, I have in front of me two acrylic tubes. This one is shaped like the vowel R. It's 17.5 centimetres long, and it sounds like this if I put the buzzer in the end.
So how does that work? How are you producing that particular sound?
Well, the way the sound is produced is because the tube itself has an internal shape which is modelled on a real human mouth.
Saying R.
Saying R. So if you imagine saying R, you open the jaw. So if you contrast R with E, E has a close jaw, R has an open jaw. And I also have a tube for E, which is the E shape sounds like this. And what's elegant?
Like you went down at the end a bit, though.
Well,
getting tired or something.
The pitch goes down because the buzz goes down. But the key thing is that the shapes are producing R and E. And what I like to remind singers, if we're talking, to singers, is that all you have to sing with is a buzz and a tube that's about 17.5 centimetres long, which is all squidgy. And that's it.
Well, let's look at something which, some people who make their money from the voice are people who take the rip out of other people and sound like people. So how are they doing that? Because that all comes down to the same business, I suppose, as to why we have accents. And I know we're now going to get a flurry of 5 million emails because people love the subject of accents. But why do I sound English, Helen sounds English, yet a lot of people on the other side of the Atlantic have their own distinct way of sounding?
Well, It's we have the basic human speech production apparatus. We all have the same larynx and a tube above it. But culturally, depending on where we're brought up and what the first sounds are we hear when we're very young, that begins to determine what we're going to sound like when we speak and indeed sing and indeed make music. So if you're trying to imitate, if you're a professional imitator, like, for example, Rory Bremner, he will take a voice and he will try and imitate that voice, but he's got a fundamental problem, and the fundamental problem is that he's got to do it with his tube and apparatus, and he will not have the same tube as the person he's trying to imitate.
Now, you spent some time with, actually, Rory Bremner, the BBC. He's often on telly, isn't he, doing this, and he was taking the rip out of Tony Blair. So you've given me a lump of Tony Blair. So here's our good old friend Tony.
It's not the consequence of foreign policy, it is an attack on our way of life.
Everyone remembers that speech very well, don't they? And here's Rory Bremner doing Tony Blair.
It's not the consequence of foreign policy, it is an attack on our way of life.
Now, what's really interesting is I can tell that's not Tony Blair, but at the same time, it does sound dramatically like him.
It does. The acoustics are different in both cases. Tony's was in a big hall and it sounds like a speech. Rory's was in a quiet studio. But he will never produce exactly the same acoustic signature. And he can't because of the shape of his own tubes are different to Tony Blair's.
So why is he fooling me to a certain extent then? Why do I know who that is instantly?
Yes, well, the key thing he seems to be doing is latching on to some key acoustic characteristics that change when Tony Blair speaks in the way that Tony Blair does it. So they're kind of his acoustic mannerisms that he uses when he speaks. And what Rory's doing is picking those up, rather like your caricature artist might draw a cartoon, big nose, and you know who it is, even though the actual picture is a sort of circle, 2 dots and a big nose.
Well, thank you very much, David Howard from the University of York. You've given me one more sample, and we'll see if anyone can recognise who this is. I don't think you'll have too much problem.
We didn't cause it. It's not the consequence of foreign policy. It's an attack on our way of life.
You're not going to get any clues because I think that's pretty obvious. But that was actually Rory Bremner imitating that particular and well-known famous actor. It is The Naked Scientists with Chris Smith, Helen Scales. We're talking about the science of music and sound this week. On the way, we'll be finding out why it is that some sounds are intolerable whilst others are really enjoyable, and how they actually influence your brain, and also the cultural basis of music. Why do we like music so much, and how does it influence the way we behave? If you'd like to join in or ask us any questions, email chris@thenakedscientist.com.
Fancy listening to The Naked Scientists in your bed, on your way to work, or even at work? Why not subscribe to our podcast? For more information, visit nakedscientist.com/podcast.
This is The Naked Scientists, and still to come, we'll be finding out from Ian Cross from the Cambridge University just how long ago our ancestors were creating music and why they did it. But first, did you know that music can give us the similar effect of taking cocaine? Or perhaps chocolate is more your drug of choice? Mira has been finding out just what effect music can have on our brains.
If you think about it, music is a pretty amazing thing. It has the ability to make us really happy, but also drive us crazy. While some people love the cheesy tracks of the Spice Girls or the hip-hop beats of Kanye West, others can hate these with a real passion. So what is it about music that has this effect on us? I spoke to Daniel Leviton from McGill University in Montreal about what music actually does to our brains.
Well, the remarkable thing about music is that it activates nearly every region of the brain that we've mapped so far. So music listening involves the auditory cortex, which is one of the first places in the brain that the music gets processed. But then it gets shuttled off, and different parts of the brain extract pitch from rhythm, from timbre and melody and harmony. Even if you're not a musician, and even if you're not aware you're doing it, the music listening experience involves the frontal lobes trying to figure out what notes are going to come next. That's how we get a sense of surprise and release in music. That kind of feeling that the composer, played a note that you really like. That experience could only happen if subconsciously your brain was trying to figure out what the composer might do. And then often when people are listening to music, we find visual cortex activation either because they're imagining movement or they're imagining watching a performer.
I think the trains and tubes are evidence enough that people are clearly daydreaming as they listen to their iPods. But now we know what the initial effect on our brain is. What is it about music that makes it so easy to stay in our heads?
I would characterize it as being constituted of multiply redundant or reinforcing cues. What I mean by that is if you're trying to remember the words, there are a lot of things that constrain them. You've got the accent structure, the melody, you've got a rhyming scheme. There are only certain words that will fit at the end of a line. And in terms of melody, you may not remember all of the notes of a melody, but if you remember that the melody starts low and it goes high, and it might be going ba-da-da-da-da-da-da-da, and you got to get from one to the other, and there's only certain notes that it could be. There's a certain aspect of human memory that's illusory. You don't remember every detail of everything, but you construct some of the details at the moment of recollection. So you fill in information that isn't actually in your memory with a plausible substitute, and this happens all the time in music.
The really amazing thing about music, though, is that it has the ability to cheer us up and really excite us. How does it do that?
We don't know what it is about music and why music does it and not, say, dogs barking. But we know something about what's going on, if not the why. What I mean is that there's a certain network of structures in the brain, in the limbic system, that begin to fire when we have a variety of pleasurable experiences. And these include taking cocaine or having an orgasm or eating chocolate. And it turns out that when people listen to music, that same network of neurons starts to fire. And these neurons help to modulate levels of dopamine in the brain. Dopamine is one of the neurotransmitters that essentially makes you feel good. So when you listen to music that you like, you get this change, this actual change of the chemical levels in your brain.
But what about the awful songs that just drive you crazy?
If you hear music that you don't like, that dopamine system won't be activated. And if you really don't like the music, your amygdala, which is the seat of the fight or flight reaction, could be activated, and you'll get really agitated, and you might start to sweat, and you might get angry. The American government drove Manuel Noriega out of his compound by playing him 36 hours of AC/DC music. That was enough to drive him to surrender. And I think we've all had that experience where you're in a shopping mall or something and they're piping in music and you wish it would just stop.
Tell me about it. There's nothing worse than an irritating song being belted in your ear. But have you ever thought you didn't like a song, say because it just didn't sound like music to you, and then found that after a while you suddenly really like it? What's that about?
If a piece of music that you hear is too simple and you can predict every move the composer makes, you might find it pleasurable on the first few listenings, but you'll rapidly tire of it. If it's a little bit difficult, though, you may not like it because you can't sense any structure. But over time, as its secrets are unlocked to you, as your brain figures it out, that gives you a sense of ownership of it or a sense of involvement that you don't get if it's all too apparent. You begin to enjoy it, and it can, in fact, become one of your favorite pieces of music.
With such a difference in the genres of music available to us, there's a real divide on what people class as good music. One rumour that goes round is that listening to classical music can have a better effect on your brain and even make you smarter. So to finish off, I had to ask him if there was any truth in this, because whilst I may listen to a bit of Mozart, my guilty pleasure is that I do blast out a little bit of the cheese every now and then.
Really, the most important factor in all of this is whether you like the music or not. If you like it, it's going to engage the pleasure centers, and if you hate it, it's going to engage the fear centers. Apart from that, there's no evidence that listening to classical is going to engage brain regions in a more sophisticated way than listening to hip-hop. If you listen to music with lyrics, you'll get different activations than music without lyrics, and music with a beat is going to give you activation in the cerebellum that you wouldn't get for music without a beat. So comparing James Brown to Enya, for example, or James Brown to Vivaldi, James has more beat, so there's going to be more rhythmic centers involved. But it would be wrong to conclude that one kind of music is preferred by the brain or is seen as better by the brain.
That was Professor Daniel Leviton explaining the regions of the brain stimulated by music and why it's so easy for songs to get stuck in our heads or for us to get annoyed by that music in shopping malls and by AC/DC.
No, I quite like AC/DC, but I'm not sure I'd like 36 hours solid.
No, I don't think so. I couldn't cope.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
You're listening to The Naked Scientist, and now it's time to welcome our next studio guest, Ian Cross from the Centre for Music and Science, based here at the University of Cambridge. Hello, Ian. Thanks so much for coming in, Ian. Now, Ian's been researching the definition of music, as well as the evolutionary origin of where music came from. So I guess my first question, Ian, is, if we had to define music, what is it?
Well, it's probably not the sound of Mozart on a CD or the sound of AC/DC on a CD. It's not just sound, it's action. And it's probably not just sound and action, but also interaction. And we find that more in traditional cultures than we find it in the West. We tend to find it very easy to think of music just as sound, something you listen to for purely pleasurable purposes. But in many other cultures, well, even in the West, music does a lot of different jobs.
So what kind of jobs does music do?
Well, very simply, you listen to a piece of music. Why are you listening to that piece of music at that particular time? Probably to regulate your own affective state, to change your mood. It's doing something there. You, let's say, sing in a choir. Why are you singing in a choir? Particularly if you don't have much of a voice. And there are many people who sing in choirs who don't have much of a voice. So why are they singing? Because of a sense of a way that music has of enhancing affiliation, of allowing a sense of community to emerge in a non-conflictual situation.
And would you say, is there a big difference between listening to music and creating music? So, I mean, I would say you're talking about the moods that music can make you feel, and listening to different types of music. You listen to very get-up-and-go music in the morning, or, quite sort of lovely, quiet, mellow music in the evening to wind yourself down. Is there a difference between the performing and the listening, do you think?
There is in our culture, and there is in many other cultures, but there are many cultures where people do and listen to music. There's no real distinction between the two. You just are musical. In the way that you have language, you have musicality. Some people are good at it, some people aren't. But everyone's kind of got it and uses it to receive and to create, to produce. And so
the music and language seem to be a very similar thing. I take it language came first and then we had music. But is music a very ancient thing? I take it must be something that's been around in human societies for a very long time.
Certainly in our culture it would seem to make sense that, yes, we had language doing a proper job first, and then we've got music coming along and kind of legging on the back of language. But actually, music is probably doing stuff we needed more or less the same time as we needed language, in terms of enabling a kind of fluidity of interaction, and particularly managing situations of social uncertainty, where no one's quite sure what's going on, situations on the edge. If people start saying something and talking about the determinants, the structure of the situation to each other, it could get out of hand. Music, in that context, in that situation, seems to act as a kind of lubricant to allow people to interact fluidly and easily without getting into conflict with each other.
What about a war dance, then?
Well, that's great, because you've got a bunch of people, all of whom are doing pretty much the same thing. OK, as a group activity, it's oriented towards the destruction of another group, but it's still a group activity.
Which do we think came first, then? Do we think that language came first and then the music cropped up? Or do you think people started making musical sounds and then developed that into something that we now call language?
I think people started making social sounds. And those social sounds eventually partial out, roughly, I think, when we get to Homo sapiens ourselves a couple of 100,000 years ago, into what we might now think of as music and language, which I would think of as complementary components of the human communicative toolkit.
And if we take a global view of music, and there's the wonderful variety there must be out there of different types of music, are there things like do we all think that the same sort of sounds are nice, or are there different kind of interpretations on what is a beautiful sound in different parts of the world?
Oh, extremely so. If we just like to play a little clip of Nadraya Balendro.
There's an easier way that the Americans could have got Noriega out,
Sounds like a traffic jam, I'm afraid. What's going on there? Tell us, Ian, what is that?
Well, what you have is a group of Central African pygmies, each with a little bark horn. Each horn can only play one note, so each person is playing only one note. So what you have is hocketing, antiphonal performance. One person, then another, then another, then another, then another.
Sort of like handbells a bit.
Exactly like handbells. You've got to be right on the button. Of course, the tuning of them is nothing like what we'd anticipate as being, good tuning.
But there must have been hundreds of them. How many were there? It's dozens and dozens, it sounded.
No, it's probably about 7.
Only about 7? That's quite amazing, actually. OK, we've got another clip. What have we got now?
I'm going to be honest and say I reckon that's probably Antipodean. Is it, Ian?
As it happens, yeah, it's from the Northern Territories. It's an example of wanga, which is music and law and history and education and all of those things. It's not just something you listen to because you think it's nice, although there's someone out there who probably does think it's nice.
And they tell stories and all those kind of things as well.
Yeah, and specify property rights. What we think of as music in that context is fulfilling a range of functions that we would assign in our culture to the judiciary and the police.
I was going to say we have a lawyer for that, but is it because it helps you to remember? Because if you put something to music, does it mean that you're more likely to get all the bits right because you know how the tune goes? And we seem to be very good at remembering how tunes go, but sometimes remembering all the intricate details can be difficult.
Yeah, that's true. The other advantage, really, of using music is that you can dispense with lawyers.
That sounds like that's always a good thing. I've got a couple of questions for you, Ian. This one comes from Connie in God Manchester. She said, why does music move us to tears?
Whole variety of reasons, but music does seem to have profound affective effects. That is, it works deeply on our emotions. Dan Levitin previously was talking about some ways in which limbic centres in the brain are activated by experience of music. But really, a lot of this probably depends on prior experience. You probably wouldn't be moved to tears by just hearing either of those two previous clips.
I don't know, I was.
Well, for 36 hours, perhaps. But you could be moved to tears simply on the basis of association between a piece of music and a particular episode in your life and a particular predisposition or preference to use a particular type of music to do things like move yourself to tears.
So it's stimulating a memory which is itself associated with some emotion, and that's why it's making you feel happy or sad.
Yeah, most likely.
I've got a question here from Katie, who emailed us saying she's interested in meditation, and she's noticed that when meditating or journeying with shamanic drumming, that her eyes do something a bit like REM movement, sort of flickering, and she wondered if that was something to do with the sound or this particular sort of sound and rhythm. Any thoughts there, Ian?
Well, not terribly certain about that. I suspect that there are certain... Well, in fact, there is evidence that there are some, what you could call musically central rhythmic structures, tempi, if you like, to which one can entrain. In fact, that's certainly the case. There are certain structures that one can link into. One can entrain one's own attentional pulse, attentional periodicities too. As to whether or not it requires to be shamanic in order for that to happen, it's another matter.
Got an email here from Katie Saxby, and she says, is it true that there's a sound that makes people want to go for a number two?
Probably not, other than assume the crash position.
Wasn't there some tests done in America by the military, though, along these lines?
Trouble is with sound, it leaks out, so it would be kind of difficult to prevent the same thing happening to your own soldiers were it to, in fact, have been efficacious. The other thing is about sound is a wonderful thing. You can diminish the effect by standing further away. And this, as a strategy, was something that didn't seem to have been envisaged by those who were trying to test this.
Thank you very much. That's Ian Cross. He's from the University of Cambridge. We have been talking about the science of sound and music. If you'd like to ask us any questions, both Ian and David Howard are still here with us. It's chris@thenakedscientist.com. Helen, I've got a question of a general nature from Thomas Ryback, and he actually listens to us from Poland. It's about fingerprints, and he says he understands that fingerprints are very, very useful because they provide you with this ability to grip surfaces better, as well as be identified. But he's wondering about the wrinkles that you see on animals, and do they effectively have a fingerprint pattern in the same way, specifically marine creatures, as our fingerprints?
Great question. Thanks very much for that. And actually, something I've looked at in myself is not maybe wrinkles, but the patterns that animals have, that fish have on their faces, and the ability to actually identify individuals. And I did a study of a huge fish called the humphead wrasse, or Maori wrasse, these beautiful big reef creatures. And by taking photographs of their patterns, these beautiful patterns, and they're called Maori wrasse because they look a bit like maybe the tattoos that New Zealand Indigenous people have on their faces. And I could actually identify individual fish and look at when they were coming to mate and how they were kind of aggregating this one particular area. So I think, yes, absolutely, fish can have these identifiable features on them. I don't know about wrinkles. The other thing we certainly have with things like whales and dolphins is that lots of things grow on them, barnacles and little bits of creatures and things like that. And people doing population assessments can also count whales by taking photographs of their tails and the nicks and crannies they have on their huge flukes as they come up to dive, and that can help you identify how many you've got in a population.
Thank you very much, Helen. Right, well, as it is the Naked Scientists, as we do every week, we have a question of the week, and here to do it, as ever, is Diana O'Carroll. Hi, Diana.
Hello,
Are you a
Chris.
musical person?
No, I was rubbish at the piano. Absolutely terrible.
You look a bit musical, though. Why is
Because I've got long hair.
Maybe you look a bit musical, I don't know. So, what are we up to this week?
Right, well, this week's question is all about the carbon footprint in our cave systems.
As I know, soluble rocks like limestone are soluble in water containing CO2, which comes from the atmosphere. If we take into account the present high amount of CO2 in the air, can we claim that nowadays caves are growing much faster than ever before in history?
So how does excess carbon make bigger holes in the ground? Here's our expert to explain.
My name's Jan Zelishevich. I'm a geologist at the University of Leicester. I work on Earth history. Carbon dioxide in the atmosphere dissolves in rainwater and produces a weak acid, carbonic acid. This weak acid reacts with rocks and other materials and can basically dissolve them. So it will take limestone, it will even take some of the unstable minerals in granites and basalts and such like, and will dissolve and neutralizing itself in the process. So one of the things that it will do is, if you have more carbon dioxide in the atmosphere, as we have now, then the level of acid in the rain therefore becomes higher, and therefore amounts and rates of this dissolution process will become greater, and in fact are currently becoming greater.
So the carbon dioxide that dissolves caves comes from the soil. Is this soil CO2 level affected by the CO2 level in the air?
My name is Dave Matty. I'm Professor of Isotope Geology in the Department of Earth Science at Royal Holloway. In answer to the question, caves are certainly formed by solution of limestone by carbonic acid, but it's not really the level of CO2 in the atmosphere that does the damage, that causes the water to be acid enough to form caves. The atmosphere at the present time contains about 390 ppm of carbon dioxide, which is about 0.03%. Which will dissolve in rain to form a very weak solution of carbonic acid. But this will only slowly dissolve limestone, but not at a sufficiently fast rate to form very large cavities or caves. What forms very large caves is the fact that they're covered by a layer of soil, and it's the formation of carbon dioxide in the soil, which can grow to quite large concentrations, sometimes up to maybe 1% or up to 4 or 5% sometimes in the more humid parts of the world. And when rainfall falls through this very carbon dioxide-rich soil zone, it forms a very strong solution of carbonic acid. And it's this very strong carbonic acid that can form cave cavities in limestone much more quickly over a period of tens to hundreds of thousands of years. So any change in the carbon dioxide level of the atmosphere, and we're currently at 390 ppm, and the models predict it might go up to perhaps 420, 430, even 450 in the next 50 years or so. This change doesn't have any impact, really, on the formation of caves. One other thing is that one of the outcomes of rising atmospheric CO2 levels is that it may affect the productivity of plants. So there may be an indirect link between rising CO2 levels and the formation of caves, because if the plant and forest canopy become more vigorous, then the soil might be expected to produce more CO2, so the caves might conceivably begin to grow a bit faster.
There's a possibility more carbon dioxide in the air can affect cave growth, but the process is just too slow to measure at the moment. Stephen from Devoncast Research also made this point and emphasised that it's easier to measure changes in corals that are submerged in the increasingly acidic water.
Rade on our forum hoped that leaving their calcified kettle in a CO2-rich air might help clean it, but it looks like you'd need a good deal of acid rain for that to work. If you're in a soft water area, it's likely that you wash your hair in slightly acidic water. But what if you don't wash your hair at all?
Hey, this is Jay Rizal from Boone, North Carolina. And I was wondering if not cutting your hair and or washing it makes it grow any slower.
And continuing on our watery theme, the following week we'll be exploring the ever-changing shorelines.
My name's Roy Lightning, and I've got a question about the tide times. I often do a lot of walking, so I like to know when the tide is right out, because I like to walk out as far as I possibly can. But when I was looking at the tide times, I thought, how do they get it so accurate? It says something like Wells Bar, low tide, 14:02. The question was really, how did they get it accurate like that, and who needs it that accurate? Because I certainly don't.
So what affects hair growth, and why do we keep such accurate tide tables? Send your answers and new questions to questionoftheweek@thenakedscientist.com or put them on our forum. That's thenakedscientist.com/forum.
Thank you very much, Diana. Another fantastic roundup.
Okay.
Look forward to what comes next week. I can't wait for the hair question, because I think that's one of the most commonly misstated, trotted out myths about chopping hair and stuff. So I'll be interested to see what the answer is to that one.
Okay.
It's Diane O'Carroll, our resident question of the weekest.
Laying the facts bare, The Naked Scientists.
This is The Naked Scientists. Now it's time to go back to Mira, who's with Hugh Hunt at the University of Cambridge, to find out what happened with this week's Kitchen Science.
Hello again, and welcome back to Kitchen Science. I'm here at the University of Cambridge with Hugh Hunt. Now, the first thing we asked you to do was to scrunch up a plastic bottle and see if the pitch of the sound changed when you blew across the top. So, Hugh, shall we have a go?
Yeah, let's have a go. Well, I've got my bottle here unscrunched, and I scrunch it.
The pitch has lowered.
Yeah, much lower. If I unscrunch it again. But if you remember, when I added water, the note went up. So there must be something more to it than just a volume change of the air inside.
Well, the second thing people at home had to do was lower the scrunched bottle into a bucket of water.
Yes, now this helps to give us a clue as to what's going on. Because if I take my unscrunched bottle and lower it into the water, no change in the note. Scrunched bottle, lower it in.
This time it's going higher.
Yes, I lowered the bottle in and the note went higher. So it's a bit of a puzzle.
So why is this happening?
Well, the way to think about it is that the air in the bottle is like a spring, because the bottle is behaving in the same way as what's called a Helmholtz resonator. And the little amount of air that's around the neck of the bottle is like a mass, and the air inside the bottle is like a spring. So we have to think of whether the spring inside the bottle, the air inside the bottle, is getting stiffer or softer.
But what does scrunching the bottle do?
Well, a perfectly round bottle is really stiff. And you can think of imagining a flat piece of paper and curving it around into a tube. Making it round makes it stiff. Well, think of the bottle in the same way. The walls of the bottle are really stiff when they're round, but when I scrunch it, I make lots of flat surfaces. And those flat surfaces, well, you can see them, they're flat surfaces. Those flat surfaces are much more bendy. So you can imagine the air inside, when the bottle was round, the air is actually pushing on a really stiff bottle. But when the bottle is scrunched, the air is pushing on a rather flexible bottle. A bit like the difference between standing on a concrete floor and standing on a trampoline.
So with the air pushing on a flexible surface, why does that change the pitch?
Well, you see, the mass in the neck plug, as we call it, is sitting on the spring of the air. And if the air is sitting on the soft walls, then you've got a mass on a soft spring rather than a mass on a stiff spring. Now, you could imagine just taking a rubber band and hook it onto a coffee cup and bounce it up and down. If the rubber band is really soft, then the frequency is lower. So if the frequency is lower, well, frequency is related to pitch. The lower the pitch, the lower the note, the lower the frequency.
So what's happening when you put it inside the water?
Well, that's good. Well, when the bottle is scrunched, the walls are really flexible. And now put your finger on here. You can actually feel the walls of the bottle moving.
It's really noticeable.
And if I unscrunch it, you don't feel the walls of the bottle moving nearly as much. No,
that's quite a big difference, actually.
So that means when you lower it into the water is helping to stop the walls from moving. But for the circular bottle, the walls aren't moving anyway, so there's no difference. But for the scrunched up bottle, the weight of the water stops the walls from moving. So suddenly, if the walls aren't moving, we're down to a smaller volume of air. And with a smaller volume of air is stiffer, so the frequency of vibration goes up, and that means the note goes up.
Okay, so when you scrunch the bottle, you're lowering the stiffness, and therefore you get a lower note. But when you dunk the bottle inside the water, you stop the walls of the bottle moving, and therefore you're increasing the stiffness, and then you get a higher note.
Yes, that's absolutely right. You can think that once you've stopped the walls moving by putting it into the water, then the reduced volume effect, the bottle is now smaller, is exactly the same as that you'd have got by reducing the volume by filling the bottle with water, which is what we did at the very beginning.
So if you're feeling musical and lacking some instruments at home, you could have a play with some bottles and see if you can change some pitch. Thanks, Hugh.
No problem at all.
That's it for Kitchen Science this week.
Thanks, Hugh and Mira. So all you need to do is play with the volume of a bottle and you can create some music. Have a look online at thenakedscientist.com/kitchen science and we'll show you how it works.
Lots more experiments like that there if you're in an experimental mood. Ian, got a question here from Deborah. She's in Boreham Wood and she says she's got Asperger's and experiences sensory overload. She says she's very distracted by repetitive sounds, but when she does this or sings this to herself, she's not bothered by it. So why should that be?
Two possible reasons. There is some evidence that people suffering from Asperger's syndrome may be orally hypersensitive, but I think the more plausible reason is likely to be that listening to something that someone else has created, it's simply not under your control. Whereas if you're producing it yourself, it obviously is. So it's likely to be a control issue here.
I've got an email here for David, I think, from Jill, who says some people have a certain kind of voice that when she listens to them makes her feel so relaxed that she could go on listening to them forever. And apparently our voice, Chris, and my voice as well, does this, which is wonderful. David, what do you think that might be?
Well, when we listen to sounds like speech, we've, of course, learnt about speech and we've had experiences in our lives that link to sound. So we've learnt the patterns of certain speech and it's associated with certain things. So if you've heard speech from other people in your past, perhaps your mum or your dad or a loved one, you're picking up those patterns in other people and it just triggers those memories.
And if we find someone intensely annoying to listen to, not just the content of what they're saying, but the way they sound, because we all know people like that. People have certain laughs, don't they? Why do we find certain voices intensely annoying?
My guess is, again, it's some sort of conditioning back to some experience in early life. Perhaps it was a teacher, it was the way they told you off, or whatever, that made you pick up that particular pattern. So it's another stored pattern, it's a memory.
Well, thanks for your email, Jill, and I'm very pleased to hear that our voices keep you relaxed, so keep on listening. I've got a question here from Bray, who says, why is it when you chew spearmint gum, you're left with that cold feeling in your mouth afterwards?
Okay, it's a chemical trick. It's a neurological trick that's being played on your nervous system by one of the chemicals which is in the gum, which is menthol, because menthol is one of the flavourants that gives spearmint its tangy taste and means that you do experience that mouth-freshening coolness when you breathe in. The way it works is that the nerve fibres that signal temperature in the mouth are in two categories. There's what are called warm fibres and cold fibres. The warm fibres increase their rate of firing to the nervous system, in other words, the number of action potentials they send along the nerve fibre, when they get warmer. Cold fibres do the opposite, so as things get cooler, they increase their firing rate, and they do this by having proteins which are in the membranes of the cell, and they change shape with temperature, and this shape change makes the nerve cell leakier to excitatory ions that can move into the cell and make it rev up, or they change in the opposite direction and they turn down the activity of the cell. Now, with menthol, this binds to this ion channel on the surface of the cell. It's an ion channel called TRPM8, and when the menthol molecule goes on, it jams it open so that more of the excitatory sodium ions can go into the cell than normal, and this makes the nerve cell fire at a higher level of activity than it would do at the temperature it would normally fire at. So in other words, it thinks it's colder than it really is. So when you take a breath of cooler air into your mouth, this lowers the temperature in the mouth a little bit, but the nerve cell thinks the temperature has dropped a lot. So you have this very, very strong sensation that your mouth has got colder.
But it actually hasn't.
No, there's not actually any sort of chemical trick going on. It's not actually making your mouth really colder. It's just you're being fooled into thinking that your mouth is cooler and fresher. And we like that sensation, which is why that kind of mint is so popular.
Absolutely.
Well, that's all we've got time for this week. Thank you very much for listening. I have to say thank you to a wonderful panel of people who helped us with this week's Science of Sound and Music. Thank you to Ian Cross, David Howard, also Daniel Levitin and Hugh Hunt, who helped us with this week's Kitchen Science, and of course our wonderful production team, Diana O'Carroll on Question of the Week, Mira Sinthalingham, Tom Sinkins, and also the wonderful Helen Scales. So thank you all very much. It's our Q&A show next week when we'll be, of course, exploring the world of chemistry, the world of astronomy, and all of your science questions. So if you have a question for us, just send it in this week. Chris@thenakedscientists.com. Have a great week. See you next time. Goodbye.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.